This is section 1.3, continuity and behavior and limits. Your I can statements for this section. I can use limits to determine the continuity of a function and apply the intermediate value theorem to a continuous function. And I can use limits to describe end behaviors of functions. So a continuous function is a graph that has no breaks, no holes, or no gaps. For a function of f of x to be continuous at the value of x is equal to c, the function must approach a unique value as x approaches c from the left and from the right. So let's say x is equal to 2. We want the values of our y, or our f of x, to approach whatever that value is from the left and from the right. So as we're getting closer and closer to x from the left, we want the values to approach our f of x value. And as we get closer and closer from the right, we also want it to approach f of x. The limit is the concept of approaching a value without necessarily reaching it. So if there's a hole in the graph, we want to be approaching a value from the left and the right, but there may not be a value where that specific hole is located. A limit is written in this form. It says the limit of f of x as x approaches c is equal to L. So as our x value is getting closer to c, our f of x value will equal L. If the f of c value does not actually have a value, we're going to see that as a hole in the graph, but we're going to be able to tell that it's getting closer from the left and from the right. So we have c down here. If we look at our x's as they get closer from both sides, there is no hole here for the value of L, but our f of x values are going to approach from the left and from the right to show us that it is continuous up to that hole in the graph. A discontinuous function is just a function that is not continuous. There's going to be something that makes it have a break, a hole, or a gap. And we have 3 different types. Our first type is an infinite discontinuity. This is a function that has values that increase or decrease indefinitely as x approaches c from the left and the right. Our graph can go down and up. One can go to negative infinity, one can go to positive infinity. We could have graphs where they go the same direction, so they both can go off to positive infinity, or they could both go to negative infinity. Any of those would be an infinite discontinuity. A jump discontinuity is a function that has 2 different values when approaching from the left and from the right. So if we are approaching from the left, this may have a value of -4, and then the function jumps up here to 3 and then goes up again. So there's a jump in our x value. We have an x value of c. It jumps from -4 all the way up to 3. So that would be a jump discontinuity. The last type is just a removable discontinuity. This is a function that has continuous everywhere except for at the hole where x is equal to c. So it's continuous on the left and the right, but there's just going to be one hole. Usually this means our function was in a fraction form, and the denominator, when it is equal to 0, will have a hole. When you're running a test for continuity, you're going to take your function of f of x, and you're going to see if it's continuous at the value of x is equal to c. You're first going to see if your f of c value exists. You're going to plug in your value of c, see if you get a f of x or a y value. Then you're going to check the limit on the left side and as it approaches from the right side. And we're going to see if they're approaching the same value, or if they're going to jump, or if it's going off to one of the infinities. So when we're doing a continuity test, the easiest thing to do is to make yourself a table. Now we want to see if our graph is continuous where x is equal to 2. So you're going to put that value in the middle. You're going to put values that are just a slight bit larger to the right and a little bit less to the left. So if we go larger, we can do 2.01 and 2.1. If we want to go smaller, we can do 1.99 and 1.9. Now all we're going to do is we're going to substitute in these x values into our function. For instance, if we substitute in 2 into our equation, we have 2 times 2 squared minus 3 times 2 minus 1, and that'll give us a value of 1. So we do know that our f of c value does exist. You would plug in the values for your other x values, and we would get the y values of 0.52 for 1.9, 0.9502 for 1.99, and our table fills in as followed. So if we take a look from the left and the right, the values from the left are getting closer to 1, the values from the right are getting closer to 1, and your value of f of c, which is f of 2, does exist. So we would say this function is continuous. We can do the same thing with this function. We're just going to make ourselves a table again. So we want to check to see if x is continuous at -3. So after we make our table, we're going to put in our x values. -3 is in the middle because that's where we're testing. We're going to put in values less than -3 to the left and greater than -3 to the right. Now if we plug in -3, this is a piecewise function, so we have to decide which piece to substitute in for. If x is equal to -3, remember this is your equal to sign, so we're going to plug it into this part of our function. So 2 minus -3 gives us a value of 5. -3.01 is also less than -3, so we're still going to plug it into that same function. 2 minus -3.1 is it's positive 5.01. And 2 minus -3.1 is going to give us a positive 5.1. But once we come over here to -2.99, now that value is actually larger than -3, so we would plug it into this function instead. So we would do 3 times -2.99 minus 2 is going to give us a value of -10.97. And if we plug in -2.9, that's going to give us a value of -10.7. As you can tell from the left, it's getting closer and closer to 5, but then to the right, it jumps from 5 down to almost -11. Because of that jump, this is a jump discontinuity. Corollary is just a theorem that has been proven, something that's proven true using theorems. And our first corollary we have is the location principle. If f of x is a continuous function and f of a and f of b have opposite signs, so that means one of them is negative and one of them is positive, then there must at least exist one value of c, where c is between a and b, where f of c is 0. So what they're saying is, if I plug in an x value of a and its y value is 0, and my x value for b has a y value that's positive, one's negative, one's positive, then somewhere between there, it had to have crossed the x-axis, so we have to have some x value in there that has a y value of 0. So we're going to determine between which consecutive integers that a real 0 exists. And we want to check values from -4 all the way to +4. So the first thing you do is make yourself a table of these values. So we make our table with values of x from -4 all the way up to +4. Then you're just going to take your x value, substitute it into the equation, and find your y values. So for instance, if we do -4 cubed minus 4 times -4 plus 2, then we're going to have a y value of -46. And if we continue filling out the table, it'll fill in as such. Now what we're going to do is we're going to look for places in the y values where we go from either negative to positive or positive to negative. If we look right here, my y value goes from a negative 13 to a positive 2. If it goes from a negative to positive, it had to have passed 0 somewhere along the way. So between the values of x is negative 3 and x is negative 2, we have to have an x value that would have a y value of 0. So we're going to have zeros between x is equal to negative 3 and x is equal to negative 2. Let's see if we have any more. We go from a positive to a negative. We go from a positive 2 to a negative 1. So between the x values of 0 and 1, there had to have been an x value where we would have a y value of 0. So we have between x is 0 and x is 1. And we go from a negative 1 to a positive value of 2 in my y values. So between those two x values, again, we have to have an x value that would have a y value of 0. So between x is 1 and x is 2, there had to have been a 0. So the three possible zeros would have to lie in this region. One of them is between negative 3 and negative 2, one of them is between 0 and 1, and one of the zeros is between 1 and 2. The end behavior of a function describes how a function behaves at either end of the graph. So if we talk about the limit on the left end, we're going to do the limit as x is approaching negative infinity, because negative infinity is all the way to the left of f of x. And we're going to talk about the right-hand limit, which is the limit as x approaches infinity of f of x. So you're going to tell me what's happening on the left side of the graph and what's happening on the right side of the graph. So if we take a look at this function, we're going to first find the limit as x approaches negative infinity, which just means we're going to look on the left side of f of x. Then we're going to find the limit as x approaches of infinity of f of x, which is on the right side. So if we look at the left side of this graph, it's going down. Limits can either go to negative infinity, positive infinity, or they can be approaching a specific value. In this case, we are going down. So the limit on the left side is going to be negative infinity. It's going down forever. On the right side of our graph, it is also going down. So the limit on the right side of our graph is also going to be negative infinity. On this function, this is our x-axis. As you can see, the graph on the left side is getting closer and closer to that x-axis, or the value of y is equal to 0. And the graph on the right side is getting closer and closer to the value of y is equal to 0, but it's not actually touching it. So when we write our limits, the limit on the left side of f of x is getting closer and closer to 0. And the limit on the right side of f of x is also approaching 0.